recording started. Welcome back. It's going to be a smaller group from now on, evidently. We're going to, for the next 2 days, have a bit of a closer look. The previous 2 days have covered sort of the what and the why of modeling. We've tried to touch on many topics that help you understand what dynamic modeling is, some elements of the different particular tasks required as part of hybrid modeling, the relationship of hybrid models to statistical models, the relationship of of dynamic models to statistical models, of dynamic models to data. We've talked about some of the different types of dynamic modeling, system dynamics modeling, agent-based modeling, and discrete event modeling. And we've discussed some of the motivations for their use. Just to list a few off the top of the head, to function as sort of learning prostheses, as Jeff likes to put it. Artifacts that sort of capture our best guesses as to what's going on out there so that we can evolve our understanding, so that they can help us understand better the evidence that's afforded to us. We also see that dynamic models can be used to help explain patterns. If we see patterns in the data that we collect, perhaps time series that we see, they can help us better explain where those patterns might be coming from. For many people, the biggest motivation for the use of these models is to be able to examine counterfactual situations that haven't been observed before. Therefore, we don't have the sort of data that we would need to build statistical models that capture the associations of different observed variables. And instead, we're asking about situations that are novel, situations that are new. Maybe it's improved, hospital in the home. Maybe it's the availability of a new, larger transitional care unit here in town. Maybe it's expansion of the capacity of a convalescent home here in the province. Maybe it's a matter of rethinking how the discharge process is accomplished to better account for the presence of ALC patients. For any of these reasons, or for these types of interventions, we may be seeing a situation going forward that's quite new, quite novel. And we need a model to help us appraise what that situation might look like and what the benefits and the costs might be associated with that new reality. That's a reality where we haven't had the luxury yet of collecting data. So it's hard to build a dashboard for what will be coming up. It's hard to create machine learning models or traditional statistical models, any sort of statistical model that's going to capture what will lie forward, because it's going to be drawing on patterns from the past about the associations that don't necessarily hold going forward. So for that reason, going forward, we want to complement our rich existing toolbox, those really valuable statistical models and machine learning models that we and many others make central use of. We want to complement it additionally with dynamic modeling. Dynamic modeling, I argued, at a most fundamental level, takes theory out of our head about what may be going on there in the world. Because up in our head, it's hard to reason about consistently, it's hard to share thoroughly with other people, and it's hard for us collectively to refine and critique. If it's up in the head and it's me arguing against you about what I think will happen, there's a lot of unexamined assumptions, a lot of sort of tacit judgments that are often tied up in my head. And I'm not awfully good at adding them up to find sort of the complete understanding about how a change, say, in the processes in the ED, say a physician greeter who sort of assesses the different patients, how that will ripple through to occupancy in wards, how it will ripple through to the number of ALC patients or the number of spots out there in long-term care facilities. To add all those things up, it's hard for us as humans to do, but it's really simple for dumb computers to do if we give them the assumptions explicitly. If we take that theory, that understanding out of our head, and we put it into a model, it can add up the consequences in ways that we can't. So these models help us think more quickly, deeply, thoroughly about the consequences of theory and help us make sense of the evidence in light of that theory. So the models serve as this single repository that brings together evidence of diverse forms, evidence from demographic change, evidence associated with the structure of the primary care system, associated with how our hospitals function, and it puts it all in one place. Together with the theory so that we can, among other things, ask what-if questions and see the consequences. So there's many other uses of these models that have been proffered, and some of them have been put here. They can point us to which data might be most valuable going forward, to which data the model is most sensitive. They can point us to issues with the robustness of statistical measures because we can test them against synthetic ground truths we see in the model. We know the full situation of the model, and we can see the degree to which they allow us to assess that situation given the sort of data we might get from the healthcare system. Given that sort of data from the model population, can we really infer with great clarity what's going on within the model? These are all uses of models. And if you go look at Josh Epstein's work or Don Burke's work, they list dozens of other uses. Great stuff. So we talked about that the last few days. The what and the why. Today, we begin a somewhat different course in both senses of that word. Today, we're going to be starting to look a little bit into the how of modeling. How is this actually conducted? You've seen glimpses of it here and there with the models. You've seen little icons and figures, but you're probably not sure what they are, how they fit together, how that model is actually built up. Well, this morning you'll be building your first model. You'll be building up sort of this model in an iterative fashion. And so we'll be seeing a little bit about the how, but we'll also be learning more about some of these processes. So when I said rather glibly that a model can point you to certain parameters to which it's really sensitive, we'll be seeing exactly how that's done in the software to remove sort of that mystery around it. We'll also be using the software to look at this process of calibration, how the model tries to take evidence about the emergent patterns out there in the world, the high-level patterns it might see in time series, and find parameter values that would best make the model match those patterns. We're going to be doing quite a bit of experimentation with these models, and we'll get some sense of the sort of data we can elicit from the models to compare with real-world data. So these are just a few of the topics that lie before us for the next 2 days. Fitting the fact that the next 2 days are dubbed a boot camp rather than merely the workshop, there's going to be a fair bit of added sort of demands on you. There's probably going to be somewhat less conceptual fire hose type work and more hands-on stuff. It's going to be the equivalent of the 20 push-ups in the morning. Well, okay, maybe the 10. But we're going to get you using the keyboard and mouse, doing things. And I'm going to actually hold off as much on the conceptual side because a lot of that has been addressed to the degree it will in this event in the past few days. So this is going to be more hands-on, more experience of model building. And again, I don't delude myself into thinking you're going to go out if you're knowing how to build models thoroughly from scratch from now on. But you're going to have a good flavor for how they get built and what's in there and how you use this toolbox. And if you look at a model built by UN or a model built by Alan, or you look at a model that came out of the examples I've given you, you'll have the ability to sort of parse what's going on there much better than the folks who left last night. Much better. So that's the plan for the next 2 days. What of yesterday? I start each morning with a reflection. What do we see yesterday? Well, there are a couple of things. Yuan Tian, the modeler at the who spoke at the over the lunch at the faculty club, discussed with us one particular model that she's been working on since earlier in the year for a couple of months now, really full time, which seeks to understand the patient-wide flow of the province-wide flow of patients. She concentrated, for the sake of illustration of the model, she concentrated on factors having to do with the ED and their impact on wards. But the model that she was showing actually has representations of and includes dynamics of community care options, people coming back and representing at the facility in the ED department. So there's much to be recommended for the model, and she showed how she could use it to ask what-if questions about a variety of types of possible changes, and you could look at outputs that indicated the gains or changes induced by these what-if scenarios. So that was one example of model, and yesterday I hit on an additional model example, which was for diabetic end-stage renal disease here in the province, a model that was designed to look not only at the care experience, but aspects of bringing people to care due to these very high burden conditions where we see high disparities in place. So those are two models that we saw yesterday. But in addition to that, we heard quite a bit about some additional topics. One of the topics was about the relationship between models on the one hand and data. And we talked about several aspects of this, how models serve as this single roof under which we can bring in multiple types of data, but how we bring that data in differs. Some of the data that we incorporate into the models in the form of parameter values. These are values told to the model. Exogenous quantities was the term we used, that are pre-specified to the model. Assume this for this value. In other cases, the way the model captures that data is through endogenous quantities. It matches the generated values for certain variables, for certain outputs, against observed data. This may be observed data over time because the model runs over time. And there, we're trying to keep the model honest, as it were, by matching it up against some historic data before we look at counterfactual situations. We're trying to make sure, develop confidence in the model by seeing how well it characterizes the existing situation before we say those key what-ifs. And we say, well, what if we did this differently? What if we do that? But we also reflected on the fact that many of the most powerful uses of models is to look into a situation, a counterfactual situation, situations where things differ and where we don't have the luxury of having the data on what the values of all parameters will be in that new situation, that novel situation. And for those cases, we have to recognize the fact that we're dealing with a situation where whatever data we put into the model, it might be it might capture the situation now, but it is possible that some of that data will change. We hope we've isolated that through endogenous processes in the model, but inevitably we're going to be dealing with a future situation where some of the patterns that we see change, maybe because of technological change we can't anticipate, maybe because of change having to do with socioeconomics or demographics that we haven't yet anticipated. And today, Anahita will be discussing a technique for keeping that model constantly refreshed with new data as it comes in, a technique known as particle filtering, keeping it sort of fresh with respect to the newest evidence as it arrives. We further, though, talked about spilling water over my sweater. Any chance one of the TAs could go get me a bit of water? Any chance another one of the TAs could go get me some paper towels? Thanks very much. Sorry for the un-TA-like task. So we further talked about the relationship between dynamic models on the one hand and statistical models on the other. Both of them are highly complementary, but they're different. Statistical models allow us to capture some of these associations using observed data. They typically have far fewer latent variables that aren't directly observed. Sometimes they do incorporate them, but they play a key role in estimating certain quantities that go into the model. But when we're asking about counterfactual situations, and often when we're asking about sort of distal, thanks so much, I really appreciate that, system-wide impacts of changes and one of their systems to see many, many outcomes, dynamic models are a tool of choice. That is the tool people look to. Oh, thanks a ton, Raheem. Sorry for the indignity of it. That's great. Thanks. So within this context, our dynamic models are tools that we use for certain types of tasks that where traditional statistical models are not well suited. And we talked about the fact that in contrast to a very common type of use of modeling in the statistical area, where we have a single dependent variable and many independent variables, within the context of dynamic modeling, we're simulating feedback loops. And often the thing that's an output, something we look at, is also serving as an input from further change. So we may be looking at, for example, number of patients who have been registered but not yet assessed within our ER, whether it's with an agent-based model or a discrete event model or a system dynamics model. We may be looking at that quantity over time, but we have to recognize the fact that that quantity is contributing to the evolution of that model. It's going to be affecting the dynamics of that model as well. Not only is it a symptom, it's a cause of change within that model. So dynamic models are full of feedbacks. And as Jeff noted, one of the techniques we're discussing, system dynamics, is particularly powerful in highlighting the role that these feedbacks play visually and drawing our attention to them. The feedbacks are there in the other sorts of modeling. It's often that we don't pay quite as much attention to them unless we're conscious about so doing. So those were some topics we discussed. We also spent some time yesterday discussing the dynamic modeling process. And one of my biggest exhortations there was to build models incrementally, step by step by step. And why? Well, let us count the ways. By building them incrementally, instead of saying, okay, we're going to build this big model for 2 years from now, we're going to get this great consultant to come in and build this model. and they're going to give it to us 2 years from now. There's no shortage where that is done. And sometimes the consultant isn't even a great one. But there's many problems with this. One of the key problems is that that model you get, even if it's delivered on time, on budget 2 years from now, it will have missed the opportunity to learn as it's being built. And often it's that experience of interacting with the model that clues us in to where the big priorities are, clues us into portions of the model we really have to attend to in more detail, portions to which it's really sensitive. It's that modeling process that gets us the biggest insight and that shapes where we want to go. And so planning on building that model up front, exactly what will be in it, is, in my view, a mistake, because it ends you up with something that's much less informed than if you had built it incrementally along the way and have learned from that process. But there's many other reasons as well. We're dealing here, ladies and gentlemen, with models of complex systems where there's complex emergent behavior. And when that model incorporates many pieces, understanding what pieces contribute what behavior after you've built the entire big model is often hard. You can do it through very careful experimentation. You can start to get insight. But it's much easier when you're building it up incrementally to see how adding one thing in changes the behavior. Another thing in changes the behavior. You get an intuition for where these behaviors are coming from. And there's a lot of learning and discovery and often redirecting the course that comes from that. But additionally, you add one thing in at a time. If something goes wrong, if you've made a mistake, you more quickly spot it. You know where the problem likely lies as well, because you've only changed one thing, and you can much more quickly sort of zero in on it. If you build that big, great model 2 years from now and you see odd behavior coming from it, you're not going to be sure up front, is that emergent behavior or could that be a bug? And it's going to take you a lot longer to tease that out than if you had built it incrementally. So those are some of the reasons to build the model incrementally. I also argue it delivers value all through. You get something back from the model all through the process. So those are some of the reflections from yesterday. Any questions related to that before we go on? Any questions related to those things we saw yesterday? Any requests from the group here about things that you'd really like to see? I mean, you have an agenda and we're rethinking with it and making some tweaks here and there, but you have some sense about what we'll be covering. Are there any things you'd like to see, you'd really like to talk about? Examples of a certain sort, particular steps in the modeling process, particular issues in how you build the model. Are there any things you'd like to see added so that we could cover them in the next 2 days? Oh, okay. Consider that an ongoing invitation. I would love it if one of you came up to me and said, I really want to see discussion of this issue, or I want to understand how it fits in with this sort of issue. I'd be glad to try to address it. Okay, so please, the next 2 days, let's see if we can make this somewhat interactive. Because if you don't make it interactive, I will. It's going to be interactive. Yes. Welcome.
I have one issue that arises out of the work I'm doing with Dylan at the moment.
Okay. Huh?
The notion of feedback within a multi-level model.
Indeed. How do you think?
Well, how do you build it? But more importantly, how do you know that feedback has occurred and is feeding back again?
That's a great question, and this question has occupied minds both great in the back of the room and mediocre in the front of the room. So it is possible to capture. It's actually fairly readily capturable. So maybe I can unpack that question, as it were, for others here. I have a disturbing sort of sense that my further wanderings may be inhibiting the quality of my audio here. So pardon me as I just check this out. Okay. I think actually we are okay. Excellent. So it's not. So I can wander, ladies and gentlemen, with abandon, and wander I will. So Joachim's question had to do with multi-level models, and the fact that sometimes we may have a model, for example, that deals with individual patients down at this level, and forgive my artistic license. These patients may be in our model in quite some numbers, but we're interested in larger level structures. It may be that we want to group these patients into families, for example. Maybe they're not patients. Maybe they're patients and caregivers. Maybe they're different individuals in a population who are at risk. We may want to group them into families, and then these families and other families may be found in, municipal groupings or towns, and indeed into health regions, and into larger groups. Or these could be patients in a ward, and these are wards, and these are areas of the hospital, whole service areas, and so on. So this is a very common need in modeling. And in fact, the tool that we're using, AnyLogic, makes building this sort of hierarchical structure quite straightforward and actually quite natural, in the sense that how it's mirrored in the model, how it's captured in the model, mirrors how it is sort of takes place in the world. We'll have a family, perhaps agent. We'll have a town agent and a health region agent, and the people will be within the family. These people within it will be a population in family, and families will be a population in towns, and so on. It's quite nice. But the question is deeper than that, about structure. The question is about dynamics. So at this high level, suppose there were some dynamic going on, some action going on at the health region level. Maybe it's staffing changes having to do with home care, for example. Maybe it's factors having to do with involving informal caregivers in the ward rounding, as Jenny Bazran has undertaken. So here, the dynamics up here might end up affecting things down here, for example, and vice versa, of course. What's going on down here will ripple through, one hopes, to the health region and send a signal that, there's needs that are not being met. So these feedbacks, can we capture them within these models? Most emphatically, and that transcends the type of model. Discrete event model is a little bit more restrictive in terms of some of the ways you can capture things, but certainly in a system dynamics model and an agent-based model, you're able to capture feedbacks like this quite readily, and sometimes in a discrete event model. So we can have these higher-level structures feedback. Now, within a system dynamics model, there'll be an actual loop in the model diagram that's indicative of a feedback. How we capture hierarchy in a system dynamics model is less pretty than an agent-based model. In fact, I find it downright aesthetically objectionable, in the sense that the variables representing these different levels are all at the same level of the model. There's no hierarchy within the model. With an agent-based model, we actually have a hierarchy that mirrors the hierarchy in the world. But in an agent-based model, this loop, this feedback, is not visible. It's there. It may be there. That this person's evolution may depend on the availability of home care. How whether an infection in their foot gets spotted in time may depend on how frequently a home care person from the health region visits them, and of course other processes at this level, but and therefore that might affect their trajectory in terms of presenting for care. But that feedback would be it's in the model. If the folks in this room will learn the tools for basically recognizing that it is there and what it does, but it won't be visually obvious. And this troubles me. And I believe the trouble associated with this extends to my elder colleague towards the back. Is that fair to say, Jeff?
Barely is true.
Okay, so I appreciate the gravity of the remark, and this feedback is often central to understanding how things are evolving. So it would be nice if it could visually accentuate the existence of this feedback. And Jeff and I, as well as some of the folks working with us, do have a hope of trying to find a way of capturing that feedback so that it's obvious in an agent-based model. Right now, it lies hidden. It lies less easily observed, but important and operable within that model. Dylan, who's helping you with your model, has found ways of visually showing things like that by adding visual elements to the model explicitly that are not themselves functional things, but rather they're illustrative. But they do bring out this the occurrence of a feedback in a way that may be visually clear. And so you might talk with him about actually putting in place the feedback so that it's evident. The problem is it won't be pulsing according to the dynamics of the model automatically. And we wish to allow for that sort of dynamics. Yes, Dylan. Well, there's a large and very interesting literature in system dynamics that's far less well known outside of system dynamics. A feature that's not limited to this particular issue, which whereby you can actually quantify the strength of a feedback, how much it's shaping the behavior of the system right now, and there are tools within the system dynamics context which actually will make an arrow visually indicate sort of how strong that feedback is, how important it is in shaping the behavior of this model. And one could extend that sort of approach logically to agent-based modeling, for example, and make that arrow pulse.
Depending on the way that any logic files things,
Yeah.
may or may not be possible in their code. So I might be able to shift the color.
Yeah.
But if it's not a pile of stuff, then it's
right.
Might be the same problem with that.
Indeed. Yeah, it's just with a bit of flexibility on their part, hopefully something will be possible. Yeah. Okay. So that was a reflection on yesterday. Any questions or comments or things people want to ask about before we get started for the day? Before we get your hands at least closer to the keyboard, I'll give one little lecture first to motivate the first example, and then we'll get your hands on the keyboard building things. Questions? Yes.
In the diagram of
Yes.
modeling, there are some boxes and lines connecting between boxes.
Yeah.
To me, those boxes are black box. So I'm wondering if there's just a probability equation inside the box, or there are actually.
Okay, so I appreciate the question. The question, as I understood it, was when you see one of these diagrams of a model, there's structure there. There's boxes and lines and so on, but you're not sure what those boxes represent. They seem to, even if they're shown as white, they're black boxes. That you're not sure what they mean. Okay, so So they mean different things for different types of modeling, but they mean something very, very specific that by clicking on it and knowing how to read it, you can understand exactly what they mean. Now, I'm wondering, are you thinking specifically about system dynamics modeling, where there's squares and links between them, that sort of thing, or any of the type? Okay, so the squares and the links between them, if we go and we were to open the Krugerian model, let's go close this out, and I am going to open up a model that we had loaded a few days ago. I'll go and highlight where it was. I'm going to take just a minute here. 2005 Service Network Bootcamp, participant resources, and live examples. It's this one SD example total value stream expansion post report. I'm going to go open that up here within a model or within the modeling software, and you folks are welcome to follow along or not as you see fit. And I'm going to go. I'm going to go to main here. We're going to be learning what these things are and how they fit together in just a little bit. And I'll go down to the sort of the main area here, this area here. Okay, so these boxes are what's called, what I turned before. Anyone remember what the name for this was? Began with an S? Stock. It's a stock. It's an accumulation. And it has an extraordinarily precise meaning, this stock, okay? To do full justice to this meaning would require to do full justice to it would require much of the morning. But this is, in mathematical terms, it's what represents an integral. The rate of change of this is equal to the value of the inflow minus the value of the outflow. Remember, I talked to you a few days ago about this idea of a bathtub. The water in the bathtub is rising if the inflow is greater than the outflow. If the water is coming in through a faucet faster than it's draining out, the level of that bathtub will be rising. If the water is going out faster than it's coming in, if like the faucet is turned off, it will be draining, it will be going down. And indeed, a generalization of that is the rate of change, how quickly it's rising or going down, is precisely given by the value of this minus the value of that. And in mathematical terms, the derivative of this, which is an indication of the rate of change, can be positive going up, negative going down. If it's big positive, it's rising quickly. If it's big negative, it's going down quickly. The rate of change of this is the inflows minus the outflows, the sum of the inflows minus the sum of the outflows. And the inflows and outflows, how do we know how they're changing? Well, they're changing according to formulas given here. So if we went and we looked at this, for example, and we looked at the triage and registration here, this process here, what we would find is that if the ED is open, we're going to have a number coming in, which is basically or a rate coming in, which is given by the value of this stock, the number of people here divided by some mean time to be seen. This door, or mean time to be registered rather, this door to reg time. Otherwise, it's 0. So in other words, otherwise no one's coming in through TRIO, through registration. So this is a formula that gives the value for this as a function of this, as well as the time of day, or whether it's open or not. Similarly, this one here is given by some number of total ED arrivals, the fraction of them that arrive at the given hour, times some intervention-related change. I think it's attaching reduction. So the formulas for these guys are given along with this flow, and the value of the stock changes as dictated by the values of the flows. We provide an initial value, and thereafter it rises or falls according to the net value of the flows. So the meaning of this should not itself be a black box. There's actually a precise mathematical meaning to it, which I could write down, but I don't want to scare people. This is what's known as a differential equation. It's actually it's a very specific mathematical construct, and it is precisely given by the rate of change of this, positive or negative, is given by the sum of the inflows minus the sum of the outflows. Jeff, do you want to comment on that at all in terms of unpacking that notion, just in case you have a different way of tending to express it? Okay. I don't know if that's helpful at all.
Does model define those differential equation or any logic?
Any logic takes care of all that stuff. You draw it out visually. It knows what its precise meaning is, and it will accordingly treat it as solving a differential equation. You don't actually have to look at the equations. You just look at the graphical depiction. But that's what the meaning is behind the scenes. The meaning is one of there's a differential equation there. So we describe it graphically. We put in formulas. It's a little bit like models are different from spreadsheets in some deep ways. If you think about it, a model shows you the structure but hides the numbers unless you want to see them. A spreadsheet shows you the numbers but hides the structure in terms of the formulas unless you want to see them. But there is certain ways in which they're similar. Like when I plug numbers into Excel and I have a formula, it takes care of calculating all those formulas, right? And in my youth, I was actually one of the programmers working on programming Excel, and I knew the guy who did that, the code to do that. He knew all about it. In fact, I spent quite a bit of time going through that code to sort of calculate things. But the people who use Excel don't have to worry about that, right? It's all taken care of for them. They put the number in, it recalculates whatever depends on it. And so it is with these models. You put in, you describe what you want to happen, what you want to be captured, sort of what the model should do, and it takes care of the how as far as making it happen, the differential equations. You don't have to look at them. Is that helpful?
Yes.
Yeah. Okay. Great questions. I appreciate it. Other questions? As far as I'm concerned, the most valuable things we could do in the next 2 days is to address, questions from you. So please keep them coming. Other questions for now? Okay. Great. So let's then go and talk a little bit about sort of a few comments related to hybrid modeling, and then I'm going to switch over to get your hands on the keyboard, build